Between the stellar and the supermassive, there is a void. Not a void of space, but a void of knowledge. A missing chapter in the universe's autobiography. For decades, we searched for what should have been there. Theories suggested their existence. Observation could not confirm it. An absence too precise to ignore. We have witnesses at both ends. The solitary hunters, 5 to 50 times the mass of our sun. The galactic architects, millions to billions of solar masses. But what lies in between? An intermediate mass range the models predict, yet nature has rarely revealed.
Mr. Kailer, is this a missing chapter or one that has never existed, waiting for us to open it and read?
Perhaps neither. Perhaps it is a chapter written in a language we have not yet learned to read. The universe does not hide its structure out of intention. It reveals itself through evidence, through motion, through gravity, through distortion. If something occupies that missing range, it will leave fingerprints, subtle shifts in stellar orbits, unexpected gravitational waves, a center of mass where no light shines. For decades, this remained one of the universe's quietest mysteries. We identified stellar remnants. We confirmed supermassive cores. But the intermediate scale has yet to be directly verified. A predicted population still awaiting decisive evidence. This is the mass gap. Stellar black holes, thousands confirmed. Supermassive black holes, hundreds confirmed. Intermediate mass black holes, 0. For decades, 0. They shouldn't be this rare, but we couldn't find them.
But couldn't is not don't exist. We just haven't looked in the right places, haven't asked the right questions.
The first clues came not from light, but from its absence. In the early 2000s, astronomers detected something strange in the galaxy Messier 82, an object emitting X-rays, but too bright for a stellar black hole, too dim for a supermassive one.
Oh, not at the center. It's not ruling a galaxy. It's just there. Detached, off-axis, yet radiating energy far beyond what a normal stellar system could produce.
That luminosity suggests sustained accretion, too powerful for a typical stellar mass black hole. Yet far below a galactic nucleus, it occupies the scale we've been searching for. HLX-1. Estimated mass, 20,000 suns. Too heavy to be born from a single star. Too light to grow without a trace. The first serious candidate for an intermediate mass black hole. The first direct trace was recorded through observation. This is a tidal disruption event. When a star wanders too close, the black hole's gravity tears it apart. The debris spirals inward, heating up to millions of degrees, screaming in X-rays. For a stellar black hole, the scream is brief. For an intermediate mass black hole, it lasts longer, bright enough to be seen across the universe.
20,000 solar masses. That's not just in between. That's a specific range. Why there? Why not 10,000? Why not 50,000?
Now you're asking the right questions, because 20,000 isn't random. It's a clue, a fingerprint, and it leads us to the next piece of the puzzle. From here, we can begin to ask the question, where do they come from? Theory 1. Hierarchical merging. In the crowded cores of globular clusters, stars collide. Small black holes merge into larger ones. Over millions of years, they grow. Not by feeding, but by marriage. A black hole wedding, repeated until it reaches the intermediate range. Each merger amplifies gravity until a single object dominates the cluster's core. At that scale, gravity stops being local. It becomes the organizing force of the entire system.
So, they are not born, they are assembled, piece by piece, in the oldest realms of the galaxy.
This is why we look for intermediate mass black hole in globular clusters. They are the smoking gun, the remnant of a violent history written in gravity. Omega Centauri, Mayol 2, 47 Tucanae, each one a crime scene waiting to be investigated. Theory 2. Direct collapse. Not all massive stars become typical stellar black holes. Some are born different, heavier, instability. When they die, they don't go quietly. Their core collapses so violently, it skips the neutron star phase entirely. A baby. This is a tidal disruption event. When a star wanders too close, the black hole's gravity tears it apart. The debris spirals inward, heating up to millions of degrees, screaming in X-rays. For a stellar black hole, the scream is brief. For an intermediate mass black hole, it lasts longer, bright enough to be seen across the universe. New _line, born in a single scream. But the collapse does not end in silence. In the seconds that follow, gravity tightens its grip. Matter that once sustained fusion is crushed beyond resistance. No stable neutron core, only a rapid implosion and a black hole, born already massive. If such an object forms inside a dense cluster, its influence is immediate. Stars begin to shift, orbits distort, energy redistributes through close encounters, and when a star drifts too near, a tidal disruption event ignites. Gravity stretches it apart, turning a sphere of plasma into a stream. The debris spirals inward, heating to millions of degrees, radiating fiercely in X-rays. For a stellar mass black hole, the flare fades quickly. For an intermediate mass black hole, it persists, longer, brighter, a signal strong enough to cross intergalactic space. Not speculation, not inference, a measurable signature of something born in a single catastrophic collapse.
Wow, what a cosmic wonder! A star turning into a black hole, even as it explodes?
This is the orphan origin. No family, no merger history, just a single catastrophic birth. These intermediate mass black hole would be rare, but they would exist, and they would be the purest form of the intermediate mass. Theory 3. Primordial seeds. What if intermediate mass black are not born from stars at all? What if they are fossils, From the first second of time, density fluctuations in the early universe, so extreme they collapsed directly into black holes before the first star ever ignited.
So they are not born from stars. They may have formed earlier, possibly before the first stars ignited. If that is true, then they are relics of the universe's first heartbeat, seeds planted in the dark, long before light had a name, while space was still cooling, while matter was still learning how to gather. These shadows were already taking shape. They did not wait for stars to die. They grew quietly, feeding on the invisible scaffolding of dark matter, pulling in primordial gas. By the time the first stars ignited, the stage had already been set. Something ancient was watching. And in that silent waiting, they shaped the galaxies that would one day call them their core.
If this is true, then every intermediate mass black is a time capsule, a message from an era we can never directly observe. They are not just missing links in the black hole family tree. They are the roots. So why are they so hard to find? 3 reasons. 1, they don't eat often. 2, when they eat, they don't shine as brightly. 3, they hide in crowded neighborhoods.
We are searching for a subtle signal within an overwhelmingly bright field, a single faint anomaly among billions of luminous sources.
An intermediate mass black does not reveal itself through light, but through its effects. It exists like an invisible conductor, never appearing on stage, yet directing the entire motion of the surrounding stars. If we map their velocities carefully enough, patterns begin to emerge. Stars near the center move faster than they should, curving around something we cannot see. Their orbits tighten, accelerate, bend under a hidden mass. It is gravity writing its signature in motion. We don't observe the black hole directly. We reconstruct it from the choreography it imposes. But we're learning to see in the dark. Better X-ray telescopes, gravitational wave detectors sensitive enough to hear their mergers. Someday soon, we'll find them. Not just one. Hundreds. And when we do, the mass gap will close forever. HLX-1. We've known it for years, but it was always alone. A single data point. Then came more. In 2019, gravitational waves detected something unusual. Not from a binary merger of stellar black holes, not from supermassive ones. Something in between. The signal didn't fit any known category. Too heavy for a stellar black hole, too light for a supermassive one. For decades, that gap was only theory. Then multiple observations, X-rays and gravitational waves converged. The missing middle wasn't hypothetical anymore. It was measurable.
142 solar masses. That's too massive to be a typical stellar black hole, yet far too small to be supermassive. This is the first definitive evidence.
The gap is closing. Not completely. Not yet. But the first thread has been pulled. The universe is finally showing us its middle children.
So we have 3 possible origins: hierarchical mergers in globular clusters, direct collapse of supermassive stars, and primordial seeds from the early universe. Which one is correct, Mr. Kailer?
Perhaps all of them. Perhaps none. The universe doesn't have to choose one path. It can take all three, and our job is not to decide which is right, but to understand how they coexist.
Then, that unopened chapter is the mystery we must confront if we are to truly understand the origin of our universe.
Intermediate mass black hole are not just a missing link. They are the hinge, the pivot point where stellar evolution meets cosmic evolution, where the death of stars connects to the birth of galaxies. They unify the story, from the first fluctuations after the Big Bang to the vast structures we see today. Without them, the timeline fractures. With them, it aligns. A continuous arc from primordial darkness to galaxies blazing with light.
Thank you for showing me the evidence was there all along.
They were always real. We just needed better eyes to see them. Between the small and the immense, between the stellar and the supermassive, there is a bridge. We cannot see it yet, but we know it's there, and one day we will cross it.